In this lecture we talk about second uniqueness theorem for primary decomposition. So say we are given this ideal I in some ring R and we have a minimal primary decomposition. So this ideal you writing as Q1 intersection Q2 all the way to Qn, and this is a minimal primary decomposition, and each of these ideals Qi is Pi primary. So that is, if you take radical of Qi you get Pi. Now if each of these Pi's, which are corresponding to Qi's, each of these Pi is minimal over the ideal I, then what we can do is, this ideal I lies in some ring R, we can construct this map R to R localized at this minimal prime ideal Pi. So you have this ideal I which lives in R, then you can talk about its extension here. So this will become an extension here, IE. So then this ideal gets mapped to IE here, then you can pull it back and then becomes IEC. So whereas it is contraction back in the ring R. So then if you do that, you first extend it, go to this ring here, localized ring here, then you contract it, come back to the ring R, you get Qi. So this Qi is corresponding to this Pi where you have localized the ring. So the extension and contraction is with respect to the localization map. Notice that this means that the chosen decomposition is not important. In any decomposition like this, if you have Qi is Pi primary, then you can always construct such a map R to RPI, irrespective of the decomposition. Whatever you have here, if it is a minimal primary decomposition and each of this is Pi primary, you can always construct a map like this. And if you extend it and contract it, you can get individual pieces back. So corresponding to Q1 there is P1 which is primary, this Q1 is P1 primary, so you can construct map R to RP1, same ideal, extend it, contract it back, and you can recover Q1. So we will prove this theorem, but this theorem crucially depends upon a lemma. So we will state the lemma first. So let Q be a P primary ideal and say S be a multiplicatively closed ring, this closed set in the ring R. So then we can consider contraction of Q in the following ring homomorphism. So you have Q here and you can construct extension, and then you can pull it back and you have extension and contraction. So it is always the case that if you this Q you extend here and you contract it back, this will always contain Q. So we can consider extension and contraction of Q in this following natural ring homomorphism from R to its localized ring, and we have localized with respect to this multiplicatively closed set S inverse of R. So we want to talk about the properties of this. So Q extension contraction, this is the entire ring R if S intersection P is non-empty. So this Q is a P primary ideal, and we are localizing with respect to this multiplicatively closed set. So there are only two cases: S intersection P is not empty and S intersection P is empty. So if S intersection P is non-empty, if I take the ideal Q, extend it and contract it back, I recover the entire ring if it is non-empty. If it is empty, then you get just the ideal Q. So now let us prove the theorem, and we will prove this lemma later. So we are given our minimal primary decomposition. So you copy this minimal primary decomposition this right here. Then we can localize this. So you localize this entire thing, all the intersections will be preserved. So this is just in general, localization will preserve such intersections. So you just localize it, S inverse R. So we are now working in this localized ring. So we can talk about the extension. So you can talk about extension. So this is extension of ideal, extension. So we have all the corresponding extensions. So once you have the extensions, so these extensions are preserved, you can contract back. So now you can contract back. So again everything is preserved. So these extensions and contractions are preserved. these intersections are preserved under extensions and contractions. So this is just generically, just going through the algorithm. So now we want to go from here. So we have gotten this extension and contraction right here. So you see extension and contraction. From here we just want this qi. So somehow this should become just qi, and to do that we will need this lemma. So now a multiplicatively closed set S we are choosing here, in which we are extending and contracting. So obviously we are going to work in this localized ring RPI, and this localized ring can only be obtained if you have your multiplicatively closed set is precisely R minus pi. So you take all the elements in this of this prime ideal pi out, you get a multiplicatively closed set. So this S becomes a multiplicatively closed set. And obviously S lies in the complement of pi. It's precisely the complement of pi in ring R. So S intersection pi is a null set. And if I is not equal to j, S intersection pj is also a null set. And this precisely follows from the fact that this if I and j are not equal, pi is not contained within pj, and this follows from the fact because each of these pi's are minimal, so they do not contain another prime ideal. So the prime ideals are not contained within each other because of the minimality right here. Therefore if you intersect it with some other prime ideal, this complement of this prime ideal, it will not be a null set. So now we are going to use the lemma. So we are working with pi here. So S intersection pj is not empty. So if this was pj, it is not empty, you recover the entire ring R. So for extension contraction you recover the entire ring. So this gives you entire ring. Next one will also give you entire ring unless you reach qi. But for qi, the corresponding prime ideal, because qi is pi primary, so the corresponding prime ideal is pi, S intersection pi is a null set. So this is a null set. So you just recover the entire q. So this q extension contraction is entire q. So instead of qi extension contraction, copy this down, you get qi, and then you go all the way again, you have r, because corresponding to every one of them you will have S intersection corresponding j is not equal to a null set. So now you have all these rings R, whose intersection will give you R, and R intersection qi will just give you qi, and that's precisely what we wanted to show. So now only thing we have to prove is this lemma. So there are two cases in the lemma. So the first case is this S intersection p is not equal to a null set. So we consider this case first. So S intersection p is not equal to a null set. You choose an element S which is common to both this multiplicatively closed set and the prime ideal. So now S would lie in P because it lies in the intersection, and P is nothing but radical of Q because Q is P primary. So we have here Q is P primary. So that essentially implies that S to the power of n lies within this ideal Q for some n a natural number. So now you consider this S inverse of Q. So in S inverse of Q, this S to the n obviously lies in Q, so this lies in the numerator, but this S also lies within S, and S is multiplicatively closed set, so S to the n also lies within this capital S. So you have Sn over Sn, which is just now 1 over 1. This would lie in S inverse of Q, but this is precisely the definition of extension. So this is precisely what extension is, as you can see here also. This is just extension. So this is extension. So you have Q here and you have Q extension here. Now Q extension contains 1. So if it contains 1, this Q extension is an ideal in S inverse of R. It contains 1, so it has to be equal to the entire thing S inverse of R. So S inverse of R is equal to this Q extended, and therefore so this is equal to the entire ring this. So if you contract back, you will recover this entire ring R. So you take S inverse of R, you contract it back, this entire thing, if you contract back, you will get R. So if you contract back this S inverse of R, you will get R. So that is what it is, extension, contraction, you get R. Now we come to the second case. So in the second case, we have S intersection P is just the null set. And for any ideal, if you first extend it and you contract it back, this will hold for any ideal in any ring homomorphism. So this is always true, irrespective. Now we have to show equality, so we will show that this Q extension contraction lies within this primary ideal Q. So what we are going to do is we are going to start with some X lying in this QEC, and we will end up showing that X lies within Q. We'll start from here and we'll end up here, which will show that QEC lies within Q. So if Q lies in Q extension and contraction, so it lies within here, it has to come from somewhere here first. Only then you can contract it back. So what is going to be the form here? So here its form is going to be something like X by 1. So X by 1 here in this form, this is extended ideal, you can write it as Q over S for some Q in this ideal Q and S in S. So obviously you can see this is precisely this S inverse of Q form, which is the Q extended. So Q over S. So this, in terms of if you think of in terms of localization, this means that you have some U, so that this UQ minus XS is equal to 0. So yeah, so basically this would mean that you have XX, then multiply this minus Q, you have to multiply by some U, so this equation will hold. So this follows from localization. So that would mean that UQ is equal to X times US, or US times X. So we are working in commutative rings, so it doesn't really matter. So Q is P primary. So since Q is P primary, so this U times Q, this lies within ideal Q, so this also lies within ideal Q. So we are saying X dot US, this lies in our ideal Q, which is P primary. So we have two cases, X is in Q or US is in P. So we want to end up showing that X is in Q, so we have to show that US does not lie in P. So US lies within S. So since US lies within S, because this S is a multiplicatively closed set, this lies in S, so this would lie in S because U lies in S and S lies in S. And since it's a multiplicatively closed set, their multiplication would also lie in S. But S intersection P is a null set, so if US lies in S, then it cannot lie in P. So US does not lie in P. So the only option left is X within Q, which we had to show.